got a drinking problem. Poor shirt. I'll try not to spill water on you later. Hydrogen transmission, distribution, and delivery. Unlike systems in place for electricity, natural gas, or gasoline, there is at present no widespread transmission and distribution system for bringing hydrogen to customers. However, the technologies needed to build such a system have already been developed and are used today in small but insignificant merchant hydrogen infrastructure, which delivers hydrogen to industrial users. Merchant hydrogen system delivers fuel at perhaps 1% of the scale needed to serve major energy markets. Because the demand for merchant hydrogen is small in energy terms and geographically sparse, a fully developed hydrogen energy system will look quite different from the merchant system. However, it could provide a technological springboard for the early phases of developing a hydrogen energy system. Description of the current industrial hydrogen transmission and distribution system. Hydrogen is widely used in the chemical industries today for oil refining, ammonia production, and methanol production. About 1.5 EJ of hydrogen is consumed each year in the United States, an amount that's expected to increase to 6 EJ a year by 2010, primarily because of higher hydrogen demand for oil refining. Although most hydrogen is produced where it's needed and consumed on site, a small fraction, termed merchant hydrogen, perhaps 5% of total production, is transported to distant users via liquid hydrogen truck, compressed gas truck, or gas pipeline. Most merchant hydrogen today is produced as a byproduct of chemical activities such as oil refining or chloralkali plants. Some is produced from steam reforming of natural gas and dedicated hydrogen production plants. The total amount of merchant hydrogen transported in the United States today could fuel a fleet of perhaps 2 to 3 million hydrogen fuel cell powered cars. Technology to safely handle these quantities of hydrogen is well established in the industrial setting. Long-distance transmission of hydrogen. It's standard commercial practice in the commercial industries today to transport large quantities of gaseous hydrogen, less than 100 million SCF a day, over long distances of greater than 100 miles at high pressure of less than 1500 psi, in pipelines specifically designed for hydrogen. Characteristics of existing hydrogen pipelines have been described in several studies. In this section, we first review some of the data in these studies, based on models developed by Christodoulou. We then calculate flow rates in hydrogen and natural gas pipelines and compare the economics of hydrogen and natural transmission. Table 4 lists high-pressure hydrogen pipelines, now in service in North America and Europe. The diameter of the largest hydrogen pipelines operating today are about 12 inches, and these pipelines are capable of transmitting 100 million SCF a day of hydrogen, enough for a fleet of about 900,000 fuel cell cars. No hydrogen embrittlement or undue safety problems have been reported for these lines. It's interesting that gaseous hydrogen pressure of less than 100 bar has been routinely handled in an air-liquid pipeline, and that the total hydrogen flow in all high-pressure transmission lines today is about 320 million SCF a day, or enough to provide fuel for a fleet of maybe 3 million hydrogen fuel cell passenger cars. Potier et al. Estimate that the capital cost of pipelines designed for hydrogen transmission would be about 50% higher than for natural gas transmission lines. The cost of installation would also be higher because special care would be needed with welds. This is consistent with earlier estimates by Leith, which showed that the capital cost of hydrogen transmission pipelines is about 40% higher than for natural gas. Pipe costs would be higher because embrittlement-resistant steels would be specified, and the pipeline diameter would perhaps be 20% larger for hydrogen to achieve the same energy flow rates. Cost of compression is also higher because about threefold more compressor power per unit of energy transmitted is needed to compress hydrogen than natural gas. Specific capital cost of hydrogen compressors is estimated to be 20 to 30% higher than the cost for those in natural gas. Despite the higher cost for the hydrogen pipeline and compressors, the overall contribution of long-distance hydrogen transmission is quite small for high pressure and flow rates. Christodoulou found hydrogen transmission costs less than $1 a gigajoule for optimized 500-kilometer long or large-scale hydrogen pipelines. Potier et al. Estimated costs of 28 cents to 42 cents a gigajoule for a 100-kilometer pipeline, and Leith estimated hydrogen transmission costs of less than 15 cents a gigajoule per 100 miles of pipeline for large hydrogen flows. Although generally about 50% higher than costs for natural gas transmission, hydrogen pipeline transmission costs are still quite small compared with large-scale hydrogen production costs at $5 to $8 a gigajoule. A sample calculation comparing the cost of energy transmission in dollars per gigajoule for natural gas and hydrogen pipelines is shown in Figure 5. Assuming that the pipelines carry the same energy flow, we see that the overall cost of hydrogen transmission is 1.5 to 3-fold that for natural gas over a range of pipeline sizes. The cost of compression is an important factor, especially at very large flow rates on the scale, e.g., on the scale of total gas use in the large city in the United States. It's been proposed that the existing natural gas pipeline system might be converted to use hydrogen or hydrogen blends. One concern here is hydrogen embrittlement, that is, acceleration of crack growth when pipeline pressure is cycled. Studies conducted starting in the 70s and 80s indicate that hydrogen embrittlement of commonly used natural gas pipeline steels cannot be ruled out and could lead to accelerated crack growth and pipeline failure. Embrittlement can be avoided by coating pipes or by adding small quantities of CO, SO2, O2, or other gases. Embrittlement is avoided altogether in pipes designed for hydrogen by using types of steel not subject to embrittlement. Hydrogen can be made from a variety of feedstocks, many of which, e.g. natural gas and coal, are more easily and cost-effectively transported long distances than hydrogen itself. Hydrogen can then be made as needed at the city gate and distributed by local pipeline. Long-distance hydrogen pipelines might be used to bring large amounts of very low-cost hydrogen, or produced where feedstock costs are exceptionally low, to a region where such feedstocks are absent or are costly to import. This would be true for PEM as well. If moving hydrogen is this difficult, then electricity is not hard to move, so you can just put up a PEM and just do it that way too. It would be local pipeline distribution of hydrogen. It would be technically feasible to build a local pipeline system for gaseous hydrogen distribution. Consider the case of hydrogen distribution for use in vehicles. Here, the distribution system would not be as widespread as the current natural gas utility network, which reaches individual homes as well as industrial customers. Instead of serving every building, as with natural gas, hydrogen would be piped to a small number of refueling stations located among major roads, where a number of vehicles are refueled, as with gasoline today. For combined heat and power applications in buildings, a more extensive distribution system might be needed. The cost of local hydrogen pipeline distribution for vehicle fuel has been estimated. Installed costs for local hydrogen pipeline operations from central hydrogen production sites to refueling stations can be estimated as a function of pipeline length Installed costs for local hydrogen pipelines operating from central hydrogen production sites to refueling stations can be estimated as a function of the pipeline length and number of vehicles served. Pipeline capital costs vary from $250,000 to $1 million a mile, depending on the terrain and the level of urbanization. In highly developed areas, such as the urban United States, installed pipeline capital costs for a small 3 to 6 inch diameter pipeline are about $1 million a mile. In flat rural areas, pipeline costs can be much lower, perhaps $250,000 a mile. In developing countries, lower labor costs may bring the total installed cost for small-scale pipelines. In the United States, 15 to 20% of the total installed cost is up for pipeline labor, and another 15 to 20% is for engineering services for a pipeline through flat terrain costing $500,000 a mile. The cost of hydrogen delivery varies from less than a gigajoule for high flow rates and short pipeline lengths to $10 a gigajoule for small flow rates and long distances. Pipeline delivery is favored for short distances and large flow rates. I would be interested to see what Germany is doing to get around the embrittlement issue, if anything. Consider the distribution of hydrogen transportation fuel via a pipeline network from a central production plant throughout a city or region. Figure 7 shows the cost of local hydrogen pipeline distribution as a function of vehicle population density, cars per square mile, and pipeline capital costs. Let's assume the network of 3-inch diameter hydrogen pipeline radiating from a central plant is built. Along each spoke of the pipeline network, a series of refueling stations are located, each serving maybe 600 cars a day. Hydrogen storage at the central plant is used to meet fluctuating demands throughout the day. The extent of the required pipeline system, the length of each spoke, depends on the geographic concentration of the demand. Assuming that the cost of the pipeline is $1 million a mile, Figure 7 shows that local distribution can cost $2 to $5 a gigajoule, depending on the density of the cars. We find that a geographically concentrated demand is needed to bring down the cost of hydrogen local pipeline distribution. This graph illustrates the cost benefits of building up a geographically concentrated demand before implementing centralized hydrogen production dedicated to vehicles. At vehicle densities of less than 300 cars a square mile, 300 cars a square mile is the equivalent to about 10% of the vehicle population in a typical urban area of the United States. The cost of a pipeline transmission rises rapidly, and 10% of the vehicle population, the cost of the pipeline transmission rises rapidly, and other distribution methods, liquid hydrogen trucks, or strategies of on-site production may give lower delivered hydrogen cost. Moving beyond transportation markets into home heating or combined heat and power could involve considerably more infrastructure development. Bringing hydrogen to every household would involve a larger pipe network, handling perhaps tenfold the energy flow rate of transportation fuel distribution system. It's been suggested that hydrogen could be used in existing utility distribution systems for natural gas, either as a pure hydrogen or as an additive to natural gas. Much of the published work on using hydrogen and hydrogen blends and the existing natural gas distribution system was carried out by the Institute of Gas Technology, or IGT. Starting in the 70s, their results were summarized in a recent article by Blazik et al. The IGT studies showed that hydrogen blends in any proportion up to 100% hydrogen could be used in local distribution systems with relatively minor changes, such as replacing seals in meters. In-use systems would have to be changed at hydrogen concentrations of perhaps 15 to 20% hydrogen by volume. This is what Germany is contesting technically. They are testing 20% by volume without changes in user stuff. Increasing the use of plastic piping in local natural gas distribution systems is potentially a cause for concern because hydrogen permeates the pipe 4 to 6-fold as readily as natural gas. A similar study was done recently of a gas distribution system in the city of Munich, or München. The authors found no technical barriers to using 100% hydrogen in existing low-pressure natural gas distribution systems. Little change in NOx or CO2 emissions from the utility system was seen at 5% hydrogen by volume. Significant reductions in NOx and CO2 were seen with hydrogen percentages greater than 60%. It was observed that less than 60% hydrogen could be used in the Munich gas distribution system with no regulatory changes. The high proportion of hydrogen is allowed under existing safety laws because manufactured gas rich in hydrogen was used in the gas system until the 70s. The authors suggest that percentages of less than 60% hydrogen can be used for environmental reasons. For hydrogen vehicles, it's likely that pure hydrogen distribution network would be developed along major highways rather than converting the natural gas system. For home hydrogen energy in existing buildings, conversion or adoptions of the existing natural gas system might be considered. For new construction, there would be several options for providing heat and electricity. The choice here would be decentralized electricity and heat production versus centralized production and with distribution. It's interesting that this seems to contradict what he said, or what was written earlier about not being able to use hydrogen. Gaseous hydrogen refueling stations. The technologies to compress, store, and dispense gaseous hydrogen to vehicles are commercially available. Many are analogous to existing systems for compressed natural gas vehicles. Ongoing hydrogen vehicle demonstrations include gaseous hydrogen refueling stations. For example, Air Products and Chemicals Inc. is providing hydrogen for fuel cell-powered public transit buses in Chicago and a small system with delivery of liquid hydrogen which is then vaporized to provide gas at pressures of 3,000 psi. Electrolyzer Inc. is providing hydrogen to fuel cell buses in British Columbia, Canada, and other gaseous hydrogen refueling systems are operating at the University of California, Riverside, at Xerox in Canoga Park, California, and at the Schatz Energy Center in Humboldt, California. More such systems are planned as part of the recently announced California Fuel Cell Initiative. For a pipeline hydrogen system, a gaseous hydrogen refueling station is projected to add $4 to $6 a gigajoule to the delivered cost of hydrogen.